All right. Hey, welcome. I'm Brett Jefferson. I work at Pacific Northwest National Lab as a data scientist. And today we're going to talk about the anti-Rips complex. So if you're not familiar, we as mathematicians and topologists like to build these spaces called simplicial complexes. And these are thought of as subsets of a larger space such that they're closed under the deletion of elements. And what that means is that I've got a subset that's in my topology, in my simplicial complex, then every subset of that subset is also in the simplicial complex. So it's just kind of like a completeness kind of theorem or a completeness idea. Now let's suppose we have a metric space, and it's not hard to think. So I've got some data, maybe some weights and heights of different people, and I put a metric on that space. So something like the simple difference between the weights, or the difference between the heights, or Euclidean distance between the weights and heights. So if I've got a metric space and some points, we will create the Vietoris Rips complex. And so this is how we build a simplicial complex, is by making some statement about how to build each simplex in the simplicial complex, or each subset in the simplicial complex. And for metric spaces, we consider all pairwise distances. And whenever they're all below some threshold, or everything is sufficiently close to one another, then we say that that's our simplex. And this is our Vietoris Rips complex. So it's a really natural way to build a simplicial complex out of a metric space. And for today's talk, I kind of go through a pipeline where I build a complex, and then I jump immediately to persistent homology, or I compute the persistent homology of that space. And that's can be thought of as gaps or holes in the metric space. So this picture over to the bottom right, I've got 4 holes in this space, and these points might be some data points that live on the boundary of that hole. And so I'll compute these holes. So a really easy example, I'm going to take 25 points sampled from a circle. I added a tiny bit of noise, so they're not exactly uniformly sampled, but there's a tiny bit of noise that we can't even perceive because we're just humans. And I build a simplicial complex by first saying, okay, what threshold do I need, or how close is close for points to form a subset. Here, the distance is just long enough so that pairwise points most of the time create an edge. We can see that 12 and 13 were not quite close enough to create an edge, but all these points were. And over time, I'm going to increase that threshold. So I increase it just a little bit, enough to get the 12 and 13, but that also got me 6 to 4, so I got a chord here. And in fact, I created a circle or a hole in my space. And eventually, I connect so many things that there are no real holes here. And 3 points, we'll use this convention that 3 points don't create a hole. And in fact, it creates a filled-in triangle. So this point all the way to the right here is a bunch of triangles all overlaid on top of each other for all these different points that I sampled from the circle. In the top right, I've built what's called a persistence diagram. What this represents is that over time, as I change my threshold, I eventually create a hole, or a one-dimensional hole, and there are 2-dimensional holes and 3-dimensional holes, etc. But let's focus just on one-dimensional holes. As I increase the threshold, at some point, this hole is born. And then if I go long enough, that hole is filled in. And so that's the death time, our birth and death times. And I use these diagrams throughout the talk to just show the pipeline that we care about. And here's a second example. We might take several points from, I just sample from the square. So 0, 1, 0, 1, I sampled a bunch of points. I create, I move the threshold. And for this one, we create a cycle or a hole at at this threshold, 0.33469, et cetera. And that hole dies eventually at 0.3856. And so these are just a couple of examples of computing holes in the space and computing my persistence homology in the space. And here's the persistence diagram to match that. And I've only drawn 2 of the holes here, but there's 2 more apparently somewhere that are tiny. Okay. So why do we do this? Why am I taking this pipeline? Well, homology and these simplicial complexes tell us a lot about the structure of various data. So if my point are a bunch of cute fuzzy animals, I might build the simplex of these cute fuzzy animals, and then that will tell something about how different animals cluster together. It will also tell me about where gaps are. It could also tell me where some missing data might be. So am I missing any animals here? Maybe I prefer for there not to be any gaps in my data. So computing the homology might tell me where gaps are. Homology also can tell us something about what dimension this data live in, right? So if I take all my fuzzy animals and I get a 3-dimensional hole, well, maybe I should use 3 dimensions to model my animals. And another thing is basically dimensions of the data. So if I look at this kind of multi-dimensional scaling representation of the data, I might say that, okay, sheep, fox, the sheep, cat, fox, dog create a whole. Okay, so I go back and I say, well, the sheep, fox might be 1 dimension, right? These are the antipoles on the whole. And maybe those are like barnyard animals. And then the 2, 0, or dog, cat dimension might be another dimension of my data. So these are like pets and different types of pets. So maybe it's barnyard animals versus pets is what best describe this data. Where does the toucan fit in? I'm not sure, but this is kind of an exploratory data, method. So that's our pipeline. We take our data. It might already have a metric structure. If it doesn't, then let's just go ahead and coerce it into one. Compute the Vietoris Rips complex, and then figure out the persistent homology. And I like to take this approach. And in fact, I had some code that does it. and one thing, when you're writing code as a data scientist, you forget to change different parameters. And for me, I forgot to turn off the coerce it into a metric space parameter in my code. And I made this mistake, and I tried to compute the persistent homology, and I got weird structures like this one at the bottom here, right? So everything's connected to the toucan, but really I'm getting like antipoles that are now connected, and what looks like really far distances are now connecting to one another. And computing the homology, it says, oh, it looks like this weird structure is now a hole in the space. So 0, 2, and 4, 3, whatever this is, I've created a hole. And it's not obvious why that's a hole at all to me. And so I wanted to investigate this. So here's a simpler example. It's the circle, again, near evenly spaced points. And I get structures that kind of go all the way across the circle. Man, what is going on here? And why is there a hole here? So let's go a little further. So we know that the Vietoris Rips complex creates these k simplices by taking k points and saying they all must be below some threshold. So I satisfy this inequality. So let's see, what did I do? Well, I coerced it into something like what I call coercing into a metric structure. So I took the biggest value and subtracted the entire distance matrix from that big value. And so when I go to do the Vietoris Rips complex there, is all these max values minus the distance matrix have to be less than some threshold t. Well, that's the same as saying that all of our distances have to be bigger than some value, and that value is whatever my max value is minus the threshold. So all of my distances now need to be bigger than some number or really far apart. All the pairwise points in a simplex have to be really far apart. Okay, that helps. Let's call this the mystery complex. I've been a little suggestive in that I've drawn all of my complexes as graphs, right? So whenever I have 2 points that are less than some threshold, I create an edge. And so you kind of lose where the subsets are in this point of view. But this was really useful for me to start to visualize what it is that the Vietoris Rips complex looks like. And I'm hoping it is for you too. So, in this view, I say, okay, good. I raise the threshold and then I create an edge, and now I can see my circles a little better, my holes a little better. This was really good for me. Well, it turns out that the independent set of a graph is just all those vertices such that no two vertices are adjacent. Okay, well, what does that mean? That means that no two vertices are adjacent. So I have a set of points where each pairwise point is far away, right? I don't create an edge and when they're far away or bigger than some threshold. This is kind of what we were doing, right? This is how we built our complex. And so this thing actually has a name and it's well studied. It's the independence complex. So the independence complex is exactly the simplicial complex on the graph where the vertex set is, of course, the vertex set of the graph, but each simplex are independent sets of the graph G. So, oh, this is our mystery complex. We figured it out. Yeah. So this thing is a thing. People study it. And it turns out that Engstrom also studied it, and he called it the anti-Rips complex. So, we have some distance function on the metric space, and whenever that distance function, whenever I have a collection of points where they're all far away, or the distance function gives very high values, they create a simplex. So great, awesome. We solved a little mystery. Well, independence complexes are really useful because people have studied them quite a bit. So we know something about their homotopy types, if you know about homotopy types, and people have also studied them in relationship to domination numbers and all these kind of really cool, interesting things. So this kind of opens up a new view on, like, well, there's a relationship with Vietoris Rips and these particular independence complexes, and that all I had to do is change the inequality. And just by changing the inequality, I get all this insight into some structure in that data. But I like to ask questions like, well, I had this geometric interpretation of the Rips complex that now kind of lost. So what is a cycle for the independence complex, from this metric data that I've created? And then, when I look at higher dimensional holes or cycles, what is that communicating about the data? And then when we look at homotopy equivalences, like I take some hole and I kind of deform it into another hole. Do I lose any of that geometric interpretation, or is that somehow invariant over various homotopy equivalencies? So I'm going to encourage you as a listener, and you elected to watch this video, so now you have homework. Go and solve these questions. I encourage it. So thank you for listening, and check out the next video.